So last class we discussed about the force between two parallel current carrying conductors. So before that we discussed about what happens when a current carrying conductor is placed in external magnetic field, right? So I hope you guys have revised it. So I hope you have revised these two concepts that you're able to see. Is there any doubt? So before we get started with the next concept, let's try to understand how to apply these concepts in problems. Okay. So before that, can you tell me what will be the force experienced by a current carrying conductor which is placed in external magnetic field? What is the value of it? F is equal to I into
LB sin
L
theta.
vector. Yes, it is L vector cross B vector, or you can write it as LB sin theta times n cap in terms of vector, whereas in terms of magnitude, it will be I into or B into I into L sin theta. And how is the direction of force? Since force is the result of cross product of two other vectors, this force is going to be perpendicular to both the vectors for which you're doing the cross product. I hope it is clear, right? Similarly, when we calculated the force between two parallel current carrying conductors, we got the answer as, we didn't get the force, rather we got the force per unit length. F12 divided by L is equal to F21 divided by L in terms of magnitude. And what was the value, guys? It was mu naught I1 I2 divided by 2 pi into D, where mu naught is the permeability of free space. I1 and I2 are the currents in the parallel current carrying conductors. 2 pi represents a constant and D represents the distance of separation between those parallel current carrying conductors. So having all these points in mind, let's try to solve a problem. So listen. So the horizontal component of the Earth's magnetic field at a certain place is 3 into 10 power minus 5 Tesla. And the direction of the field is from the geographic south to the geographic north. Okay. So if I take this as the north, south, east, and this as west, the direction of magnetic field is in this way. Right? A very long straight current carrying conductor carrying a steady current of 1 ampere. So I is equal to 1 ampere. What is the force per unit length on it when it is placed on a horizontal table and the direction of current is from east to west in the first case, and in the second case it is from south to north. So this is the direction of current. Okay. So there is a current carrying conductor placed here. This is the current carrying conductor, and this is the direction in which the magnetic field is there. So how to proceed, guys? How to proceed? So you're able to visualize what they're trying to say. There is a table like this. Okay, on this table, if I take this as north, south, east, and west. Okay. So I hope you guys are able to see north, south, east, and west. The current is flowing from which pole to which pole? It is flowing from south to north. So it is flowing in the upward direction. So you can have the book in front of you. So with respect to you, whichever direction you place the book, the current is away from you on the top of the, sorry, not the current, the magnetic field. The magnetic field is away from you on the top of the book. And the current is flowing in this direction. That is from right of your hand to the left. I hope you guys are doing this activity, right? Am I clear till this point?
Right. Your voice is breaking.
My voice, is it for everyone or?
It's not breaking for me, sir.
No, sir, it's not.
Rohan, can you check the connection once?
Okay, sir.
Yeah. So this is the direction of magnetic field, this is the direction of current, right? So in this case, the magnetic field and current are in which directions? Are oriented with respect to each other in what way?
Perpendicular, normal.
perpendicular, right? So when they both are going to be normal, can I say, one minute. So can I say F is equal to, when I apply the formula, F is equal to what? B into I into L sine theta. What is going to be the value of theta, guys? It is obviously going to be 90 degrees. But if you read the question carefully, they didn't ask what is the force. They asked what is the force per unit length. So length also is not given. So you can take the length to the other side so that F by L will be equal to how much? B into I into sine 90 degrees. Right? So BI sine 90 means how much is B? It is 3 into 10 power minus 5 Tesla at a particular location into is 1 ampere multiplied with sine 90. So the answer is going to be 3 into 10 power minus 5 Newton per meter. I hope this point is clear. Yes. So those many Newton per, yes. But the question, so they have asked, okay. So I want to extend this question. Can you guys tell me the direction in which the conductor would start moving if it had the possibility?
Can I repeat the question once again, sir?
I'm saying what would be the direction in which the conductor would experience force? It's simple.
Is it opposite to the direction of current?
I always told you that, see, force is going to be a cross product of two vectors. Cross product will always give you the resultant in the direction perpendicular to both the vectors. Never forget this point. I'm not sure what is confusing. So it can definitely not be in the opposite direction. It should be perpendicular to both magnetic field and current. Right? That's what the logic says, logic of cross product says. When that is going to be the case, in which direction is it going to experience force? You know the formula, guys, write it down. I into L vector cross B vector. Am I right? So force, direction of force is given. L vector cross B vector. What is the direction of L here? L takes the direction of current. So minus I cap cross
J cap.
So I cross J is K. So it is going to be minus K. So what I'm trying to say is, when you keep the book like this, if the magnetic field is in this direction and the current is in this direction, the conductor would have the tendency to move in the downward direction. So that is the direction in which it is going to experience the force. Here. So though it is not asked, I'm very particular about directions. Sometimes in the exams, they can ask you. Second, when the current flows from south to north, easy. Simple. What happens when the current is flowing from south to north pole, as happened in this scenario?
The force will first per length will be 0.
It is 0. Why is it so?
Because angle is 0.
Angle is 0. That's as simple as that, right? So that's what they would have given. The larger the when the current is flowing from south to north, theta is equal to 0 degrees. Answer is 0. Here. So this is all about the force experienced between the force experienced by current carrying conductor placed in magnetic field. Similarly, there are problems which are based on force experienced by a current carrying force between parallel current carrying conductors also. So in today's class, what I wanted to do is we will solve some problems from the exercise book back questions. So try to tell the answer for the first one. One minute. One minute. Just a minute, guys. So let's do the first problem. So there is a circular coil of wire consisting of 100 turns, each of 8 centimeter radius, and carries a current of 0.4 ampere. What is the magnitude of the magnetic field at the center? Do it fast and tell me what is the formula, guys.
Mu naught Na by 2A.
Mu naught Na by 2A. Mu naught is how much?
Power minus 7.
4 pi into 10 power minus 7.
4
Yes.
pi.
Yes, 4 pi into 10 power minus 7. Capital N is 100. I is 0.4. Radius is 8 centimeter. So make it as. So what is going to be the answer? So N is equal to 100. I is equal to 0.4. R is equal to 8 into 10 power minus 2 meter. Then what is the value of field at the center? P is equal to mu naught Ni by 2 into R. Mu naught is 4 pi into 10 power minus 7 into N is how much? 100 into I is 0.4, the whole divided by
into 8 into 10 power minus 2.
so 2 into 8 into 10 power minus 2. How much is the answer? Calculate and tell me first.
1.6 pi into 10 power minus 2.
1.65 into 10 power minus 2.
1.6, 1.6 into 10 power minus 2.
Okay, 1.6 into 10 power minus 2. So this will cancel 2 times. This will go 4 times. 0.1. I'm getting 0.1, no? 0.1 into pi. It should be
Yes, I
something.
made a mistake in calculation.
It should be 3.11 something, 3.14. Because pi is coming, no? Did anyone get the answer? Anybody? Okay, anyways, you guys know the formula, you can try it later. Okay. What about 4.2? There is a long state current carrying conductor, state current carrying wire, which carries a current of 35 ampere. What is the magnitude of the field at a point 20 centimeter away from the wire? So wherever you see the word long, long means infinitely long. So long straight wire carries a current of how much wire? 35 ampere. What is the magnitude of magnetic field at a distance of 20 centimeter from the wire? So what is the formula?
Mu naught I by 2 pi A.
U naught I by 2 pi A. So B is equal to mu naught I divided by 2 pi into A. So mu naught by 2 pi is how much? Mu naught by 4 pi is 10 power minus 7. Mu naught by 2 pi will be 2 into 10 power minus 7 into I is 35 divided by A is how much? 20 into 10 power minus 2. So 2 into 10 power minus 7 into 35 divided by 20 into 10 power minus 2. So this will go 10 times.
35 into 10 power minus 6.
35 into 10 power
Minus 6.
minus 6%. Try the next one. Try the next one. There is a long straight wire in a horizontal plane which carries a current of 50 ampere in the north to south direction. Give the magnitude and direction of B at a point 2.5 meter east of the wire. So how to solve?
Same formula, sir. Mu naught I by 2 pi a.
That's right. But here the question is about the direction also. You need to be careful. Let me see if you are able to get it. Formula is the same. Apply it fast and tell me what is the answer. Mu naught I by 2 pi a. Is there anyone who is not able to understand? Anybody who wants me to solve and show?
Sir, can you solve it, sir?
Okay. So listen. 4.3 is long again. Carries a current in the of 50 ampere, right? So carries a current of 50 ampere in the north to south direction. Give the magnitude and direction of B at a distance 2.5 meter east. So B is equal to mu naught I into dl vector cross r vector the whole divided by, okay, I'll make it like this. Here there is no dl cross r. It is going to be the same formula, mu naught I divided by 2 pi r. Again, mu naught by 2 pi is going to be 2 into 10 power minus 7 into I is how much? 50, the whole divided by r. R is how much, guys? 2.5. That is 5 by 2 in 5 by 2 meter only, no? So no need to convert the units. So 5 and this will get cancelled. 2 will go up. 4 into 10 power minus 7 into 10. That is going to be 4 into 10 power minus 6 Tesla. Did you people get this?
Yes, sir.
Okay. Now the important question is about the direction. Right? How to find the direction? See. Current is flowing from north to south. Okay. So generally common mistake what people do is they take north, this as north and this as south. That is, they take it along the z direction. Don't do that mistake. Okay. So the current is flowing from north to south as if you have kept the wire on the table. Because they have told it is in the horizontal plane. If you observe that. So this is the horizontal plane. Current is from north to south direction. And there is a point B which is at a distance of 2.5 meter in the east. Means if you hold a book in your hand, the current is towards you. Not correct. Yes, current is towards you. And the point is at a distance of 2.5 meters on the right of the current carrying wire. So how to find the direction? Tell me.
Minus j cap cross I cap.
Minus j cap cross
I cap.
I cap. What is going to be the direction?
Is it j cap, sir?
Yes, it is j cap. That's right. So it starts experiencing a force in the upward direction. So how you are supposed to write the answer is it experiences a force in the direction perpendicular to the horizontal plane in upward direction.
I have a doubt, sir.
Tell me.
The final answer should be 4 into 10 power minus 6 k cap, sir.
Yes. That is when you write it in terms of vector. Here I wrote it in terms of magnitude. I didn't put a vector symbol on top of it.
Okay, sir.
Okay, that's right. So this is 4.3. Okay. See, what you can do is you can write the answer as k cap, but k cap is not a specific thing. You need to you need to be more clear, saying that it is in the upward direction with respect to the horizontal plane. That is what they expect in the answer key. Okay, I hope you're able to
Okay,
understand
sir.
that point. Okay, so please make sure that you mention it in the answer sheet. Next, 4.4. There is a horizontal overhead power line which carries a current of 90 ampere in the east to west direction. East to west direction. What is the magnitude of the direction of magnetic field due to a current 1.5 meter below the line? So the current is in this direction. There is a point 1.5 meter just below this line. Right? They're asking what is the magnitude and direction. See, magnitude, I hope everybody can handle it, but I'm concerned about direction. Do it and tell me.
I got magnetic field as 10 power 5, sir. 10 power minus 5.
10
I
power
got
minus 5.
1.2 into 10 power minus 5 I got, sir.
1.2 into 10 power minus 5. Let me check it.
1.26. I rounded off to 1.2, sir.
Are you getting 1.26? Let me check. So how much is it? B is equal to mu naught I divided by 2 pi r. So mu naught by 2 pi is 2 into 10 power minus 7. I is how much? 90 whole divided by r is 1.5. No? So 1.5 you can write it as 3 by 2. So this will go 30 times. And this will go to the numerator 4 into 30. So 120. Right? But 120 into 10 power minus 7, or it is 1.2 into 10 power minus 5. This should be the answer. I hope this point is clear, right?
Yes, sir.
Now what about the direction?
Minus j cap, sir.
Minus?
J cap.
That's right. That is the conductor will start experiencing a force towards you. That's right. If anybody has not understood, let me explain this point. This is east, west, current is flowing from right to left, and 1.5 meter below the line. So current is in this direction, point is in the downward direction. Ideal cross R, the direction of force will be towards us. So how much is this? This is minus I cap. This is minus K cap. So minus I cap cross minus K cap is going to give you minus J cap. Minus J cap is something towards you. Clear? So this is 4.4. What about 4.5? What is the magnitude of the magnetic force per unit length on a wire carrying a current of 8 ampere and making an angle of 30 degrees with the direction of uniform magnetic field of 0.15 Tesla? How to solve this?
Can you use that force formula, sir? That BI sine theta, that one.
Yeah, that's what you need to use. So F is equal to BIL sine theta. But the question is, you need to be very careful. They're not asking about force.
It could be I sin theta.
They're asking force per unit length.
Yes, sir. So F by L is equal to BI sine theta. We get
Yes. F by L is equal to BI sine theta. B is how much? 0.15. I is 8. So 0.15 into 8 is how much? It's 9. Sorry, 1.2. 15 eighths is 120. So 2 decimals to the left, 1.2. 1.2 into sine 30. Sine 30 is how much?
0.6, sir.
0.6. What is the answer?
10 per
0.6.
meter.
Yes. So F by L is equal to BI sine theta. F is how much? Sorry, B is 0.15. I is 8 into sine 30 is half. So that is going to give you 0.6 Newton per. Here we need not be concerned about direction because nothing is mentioned about the direction of current and magnetic field. So we need not find it. Next, let's try 4.6. A 3 centimeter wire carrying a current of 10 ampere is placed inside a solenoid perpendicular to its axis. The magnetic field inside the solenoid is given to be 0.27 Tesla. What is the magnetic force on the wire? Can you solve this?
So I got 8.1 into 10 power minus 2 Newton, sir.
So could you do this question?
Okay. So there is a solenoid. Okay, as of now, you need not worry about what the solenoid is. So this is the axis of the solenoid. Okay. So inside the solenoid, how much is the value of magnetic field? It is 0.27 Tesla. I hope that point is clear. So B is equal to 0.27 Tesla. Okay. The magnet length of the wire is 3 centimeter. And what is the value of current that is flowing? It is 10 ampere. Now the magnetic, so what is the magnetic force? F is equal to BIL sin theta, that's it. So B is how much? 0.27. I is 10. L is 3 into 10 power minus 2. Sin theta is how much? Theta is 90 degrees.
90. So 1.
1. So 0.27 into 3 is 0.81. 0.81 into 10 power minus 2 into 10 is 0.81 into 10 power minus 1. So 0.81 into 10 power minus 1 Newton is the answer. Clear? Is everyone clear with this?
Clear. Sir.
Anyone have? Okay. Anyone else having a doubt? Because I'm going to erase it. Okay. So let's look at 4.7, guys. Two long and parallel straight wires A and B carrying currents of 8 ampere and 5 ampere in the same direction are separated by a distance of 4 centimeter. Estimate the force on a 10 centimeter section of wire A. So here we need to understand there are two wires and both the wires are long, means infinite length wires, and they are parallel to each other and they are carrying currents in the same direction. So what is the distance of separation between them? 4
4 into
centimeter.
10 power minus
4 into 10 power minus 2. So I1 is 8 ampere. So what is the data you are going to collect, guys? I1 is 8 ampere. I2 is 5 ampere. Then distance is equal to 4 into 10 power minus 2 meter. Estimate the force on a 10 centimeter section of a wire. So we know the formula for force per unit length. What is the formula for force per unit length? It is mu naught I1 I2 divided by 2 pi into D. So mu naught I1 I2 divided by 2 pi into D. Observe the question. It is not force per unit length. They have given the section of the length on which the force is to be calculated. So L, if you substitute 10 centimeter, take L to the other side and do the remaining calculations and tell me the answer.
So it's a 2 into 10 power minus 5 Newton.
2 into?
10 power minus 5 Newton.
I'm not sure. Anyone else who has solved this? See, mu naught by 2 pi is 2 into 10 power minus 7. Correct? Mu naught by
Yes.
2 pi is 2 into 10 power minus 7. I1 into I2 is going to give you 40 divided by the distance of separation between them is 4 into 10 power minus 2. This and this will get cancelled, 10. And you have another 10 centimeter, that is 10 power minus 1 meter. So this is 10 times. And this is going to be 10 power minus 5. So 2 into 10 power minus 4 into 10 power minus 1. You told 2 into 10 power minus 5, right?
Yes.
That's right. So 2 into 10 power minus 5 Newton is the right answer. Let's do the 11th problem. So let's do the 11th problem. So there is a chamber in which a uniform magnetic field of 6.5 Gauss, that is 6 into 10 power minus 4 Tesla, is maintained. So an electron is shot into the field with a speed of 4.8 into 10 power 6 meters per second, normal to the field. Okay, before I proceed, I want to ask one more question. In the previous question, will those two conductors get attracted or repelled?
Be repelled, sir.
What did they say in the previous question? 8
They
ampere and
attract.
5. They both are flowing in the same direction. Last class I told you, no?
Yes, sir.
When current is flowing in the same direction, then the conductors tend to get attracted. Okay. So here there is a chamber in which a uniform magnetic field of 6.5 into 10 power minus 4 Tesla. See, generally Gauss is the CGS unit of magnetic field. You can make a note of it. G stands for Gauss. GAUSS. The same as the Gauss law. Okay, 1 Gauss is 10 power minus 4 Tesla is maintained. There is an electron which is shot to the field with a speed of 4.8 into 10 power 6 meter per second, normal to the field. Explain why the path of the electron is a circle. Determine the radius of the circular orbit. You guys know this? So whenever a charged particle is projected normal to the field, what is going to happen to it?
It moves in a uniform
It'll
circular
experience force.
path.
It experiences a force which is perpendicular to both velocity and magnetic field. And yes, that's right. It starts moving in a circular path, and the motion is considered to be uniform circular motion. So for any particle to be in a circular path, what is the necessary force?
Centripetal.
So if you equate that centripetal force to the magnetic force, you will be able to get the radius of the circular orbit, right? So it's a one-step derivation, but still you can use it as a formula also. What is the formula, guys? R is equal to m into v divided by
QB.
m into v divided by q into b. That's right. So write it down. So mass of the particle is given 9.1 into 10 power minus 31. Velocity of the particle is 4.8 into 10 power 6 meters per second. Charge is 1.5 into 10 power minus 19. B is how much? 6.5 into 10 power minus 4. So R is equal to m into v divided by q into. All the 4 parameters are given. Your work is only to substitute and find the required answer. I hope that part you can do it, right? So that part I'm leaving it to you. It's a conceptual question. Next, in exercise 4.11, that is in this problem, obtain the frequency of revolution of the electron in the circular orbit. Does the answer depend on the speed of the electron? So for this, if you recollect, we calculated the time period of a particle in circular motion. Can you guys refer your notes and tell me? Time period is equal to
2 pi m by QB.
it is 2 pi m divided by q into b. And what about the frequency? It is qb divided by 2 pi m, the reciprocal of time period. And I told you there is a name for this frequency also. What is it? It's called as?
Cyclotron frequency.
That's right. It's called a cyclotron frequency. So now again, you know the charge, you know the magnetic field, and you know the mass of the particle. So everything you're going to substitute in this, you're going to get the frequency. So that's the frequency of revolution of the electron in the circular orbit. Second part of the question. Does the answer depend on the speed of the electron? Look at the expression.
No,
Won't,
sir. No, sir,
It does
because
depend on the speed of the
no
electron.
velocity is given.
Yes. So what happens is with whatever speed you project the particle, please make a note of this point. With whatever speed we project the particle, into the uniform magnetic field, in the perpendicular direction of it, the time period of the particle and its frequency always remain as a constant.
So can you repeat that whole thing once again, sir?
See, I told when any particle is projected with velocity, when a particle is projected with any velocity into a magnetic field in the direction perpendicular to it, the time period of the particle and its frequency always remains as a constant. Okay. Means frequency and time period are independent of speed is what I'm trying to say. Let's try the 13th question. So there is a circular coil. 1 minute, let me see if you can do it. 3 lines make an angle 60 degrees. No, I cannot do this. Not taught this concept. Okay, we'll go to the next one. We'll go to the next concept, that is torque acting on a current carrying loop or a magnetic dipole. I have to switch off my camera. I'll write it and show. So write down the heading, guys. Torque acting on a current carrying loop, which can also be called as a magnetic dipole. Okay. Let me explain what this means. Listen to this. Suppose I have a current carrying loop like this. I have a current carrying loop like this. I have a current carrying loop like this. If you observe, in the first scenario, it is a circular current carrying loop. Here, it can be a square, or I can even expand it and make it as a rectangle. As of now, accepted. Okay, this is going to be ellipse, right? And for that matter, if it takes any random shape like this also, there's a very important point, concentrate, okay? Suppose the current is flowing in the clockwise direction, then which pole are we facing? I think I've explained this concept already. I did. Okay. So if the current is flowing in clockwise direction, on that. Yes. So if the current is flowing in clockwise direction, then what pole are we going to see? It is going to be something like this. So what is it? It stands for yes. So when the current is flowing in any loop in the clockwise direction, we are facing the south pole. So with a similar idea, if I take the current to be flowing in the anti-clockwise direction, Okay, if I take the current to be flowing in the anti-clockwise direction, then you will be able to see the north pole. Okay, are you guys able to understand? So why it is so, I'll explain it. Did you guys make a note of these 2 points?
Yes, sir.
Yes, sir.
Okay. Now, applying the same logic here, if I say the current in the square loop is in the clockwise direction, then it behaves like the south pole. Let's say in this ellipse, the current is in the anti-clockwise direction, then it behaves like the north pole. Okay. Let's think of the logic. So let's think what is going to be the logic involved behind this. Okay. Suppose, see, tell me one thing. What is the direction of magnetic field? Magnetic field is from the north pole towards the south pole. So if I take this as a bar magnet, for example, there is a bar magnet. Then if I take this as the north pole and this as the south pole, what is the direction of magnetic field? It's from the north pole to south outside the magnet, and inside it is from south to north. I hope this point is clear to everyone, right? Everybody knows this point from your lower grades, right? There is nothing new in this. So north pole, let's give a different understanding to it. So instead of saying that the magnetic field is away from the north pole to the south pole, can I put it like this? North pole has the tendency to emit the magnetic field lines, and south pole has the tendency to receive the magnetic field lines. Can I put it like this? Right? Outside the magnet, north pole is what is emitting, and south pole is what is receiving the emitter times. And inside, what is happening? The south pole is emitting, and the north pole is receiving. That is happening inside the magnet. Suppose I take the same logic. If I take my mobile phone, okay, which is in the shape of rectangle. So when you take the current to flow in the clockwise direction like this, if I say the current is flowing in the clockwise direction, then what pole did I say? You're able to see. Check your notes. Current flowing in any loop in the clockwise direction is going to show you this as the
South pole.
south pole. But why is it so? Because when the current is flowing in the loop, especially when you have a circular or any loop for that matter, how to find the direction is the simpler way. So what is the how do you find the direction of magnetic field using the right hand thumb rule, right? So when I place my thumb at the top in this direction and curl my fingers are going towards the mobile, accepted? My fingers are going towards the mobile. So when my fingers are going towards the mobile, the magnetic field lines are going towards the mobile. Now tell me, which pole has the tendency to receive the magnetic fields?
South pole.
Are you able to understand? There is a logic for it, right? So you can ask me, is it going to be the same thing when you take this side? You can try and see. If I keep my thumb like this and curl my fingers, again my fingers are going towards the mobile. Again I take the bottom, this direction. So I curl my fingers, it is going towards this direction, it is upward. Take it like this, curl the fingers, it is going towards the mobile. So it is acting like the south pole. So this mobile, when I see from the back of it, I am able to see that the current is flowing in the clockwise direction. Have it in your mind. If I flip the same mobile like this, then when the current in this side was flowing in the anti-clockwise direction, when you see it from the other side, what is going to be the direction in which it is going to flow?
Anti-clockwise.
Anti-clockwise direction. So when it is anti-clockwise, the current is in this way. If you want, see, you are seeing through a path, you can see them in reverse. So what I suggest you can do it along with me. If you have any, you can take your book itself as an example. Okay. So if the current is flowing in anti-clockwise direction, take your thumb and place it in the direction and curl the fingers. So with respect to this side, my fingers are coming out of the plane. Right? Which pole has the tendency to emit the electric field lines? Obviously, North pole. So what I'm trying to say is, same loop. I didn't take different mobiles. Same loop, right? When you see from one side the current is flowing in anti-clockwise direction, you see the same thing from the other side that is going to be in clockwise direction. Means if one side is acting like south pole, exactly on the other side you will have the north pole for the same loop, right? So it now think and tell me, is it necessary that this loop has to be only in the shape of a rectangle? For that matter, it can be of any shape. When you take a conductor of any shape, provided it is in the form of a closed loop, obviously, then the current which is flowing in clockwise direction will generate the north pole, and the current which is flowing, current which is flowing in the clockwise direction will generate the south pole, and the current which is flowing in the anti-clockwise direction will produce the north pole. Clear, guys? And that is the reason why within the same conductor, since you have the north pole and south pole on either sides of it, every current carrying loop. Okay, here there are two words that we are going to use repeatedly. One is called as a current carrying conductor. When I use the word conductor, I mean that it is a open conductor. A straight wire is a conductor, whereas a circle is a loop. Okay, so a current, that is why I'm stressing on this point again. When you talk about a current carrying conductor placed in external magnetic field, it experiences force. I repeat, till now we discussed no, F is equal to BIL sin theta. If you see everywhere, the topic will be current carrying conductor placed in external magnetic field will experience force. Now the next question is, what will happen if you place a current carrying loop in magnetic field? What is going to happen next? When you place a current carrying
force.
it will experience torque. Now I'm going to create a similarity of what you already know. In electric field, there was a concept, you guys remember? In electric field, there is a concept where you place an electric dipole in external electric field, it starts experiencing
Torque when it is in equilibrium, and rotatory and translation motion when it is not in equilibrium.
It is not in equilibrium. It will experience a torque of how much value? PE sin theta. You guys remember that? So when an electric dipole is placed in external electric field, it experiences torque. In a similar way, with respect to a current carrying conductor, see, there are two types of magnetic dipoles we can always talk about. What is a magnetic dipole basically? Magnetic is something which exhibits magnetic properties. Dipole, two polarities. So if I take a bar magnet, if I take a horseshoe magnet, all these things are dipoles. Those are all permanent magnets, but not necessarily that you're going to always use a permanent magnet. Now, since we saw that a current carrying conductor, current carrying loop, a current carrying loop itself has north and the south pole on either sides, can I say that the current carrying loop is also a magnetic dipole? Guys, are you able to understand this point? Current carrying loop, when you see from one side, you're able to see south pole. Exactly, you see from the back side, you will be able to see north pole. This will happen for every loop of any shape. When this is going to happen, can I say that a current carrying loop is a magnetic dipole? Accepted or not?
Yes, sir.
So when you place that magnetic dipole in external magnetic field, what do you think is going to happen? It starts experiencing torque. So what is the net effect of torque, an unbalanced torque? What will happen to the system? Wherever you hear the word torque, what comes to your mind? The object
Equilibrium,
starts
rotating.
it will start rotating. So wherever you see the word force, the object will have translatory motion. Wherever you see torque, the object will have a rotational motion. So what I'm trying to say is, when you place a magnet, that is, if this is a bar magnet, I take this bar magnet and place it in an external magnetic field. It starts revolving. Okay, it starts revolving, and that is happening purely because of the torque experienced by it. How much is the value of torque? That we will see it in the next class. Because I need some time to derive it. But tell me one thing, is it clear till this point? Are you guys clear with?
Yes, sir.
Okay, so that's what the topic is. I want you all to make a note of this. This is going to be the next topic. That is torque on a current carrying loop or a magnetic dipole. This is going to be our topic of discussion tomorrow. Before that, can you tell me where will we use this concept as? When I say a current carrying loop is a magnetic dipole, what is it we are going to achieve by making it revolve? Where do we apply it? Any idea?
We use it for inducing or something.
Inducing, you will not do it here. Inducing means you will not apply current itself. When you say inducing, you will induce current, you will generate current. Here we don't induce. I'll give you a real-time example. You have seen an ammeter, right? An ammeter, voltmeter, galvanometer, all these things. All these, if you talk about an analog one, not a digital, if you talk about an analog one, what happens to the pointer? How is an ammeter able to measure the value of current? When you pass current, no, the pointer will start revolving, it will stop at a particular point. How is it knowing that this is the value of current that is flowing through? Are you guys able to think? I don't want an answer. Are you guys able to think of this? Right. So when current is flowing through it, that current, there will be a current carrying coil inside. That coil will be placed in external magnetic field, and due to the external magnetic field, that coil will start revolving, which will turn the pointer as well. Are you able to understand? So exactly based on the amount of current that is flowing through the coil, the pointer will stop at a particular location. Okay.
Yes.
So it has an application. It has an application, which is in this chapter you will learn it under the name of a galvanometer. That's it. So in last chapter we would have seen it in Wheatstone Bridge. I would have told you what a galvanometer is, but here we will see what we will properly see what a galvanometer consists of and how it works. Okay. So that's the end of discussion for today. Any other doubt, guys, from today's class?
No doubt, sir.
Okay, if there is no other doubt, you can leave.
Thank you,
Thank you,
sir.
Wind up this session.
Thank you, sir.